Okay, thank you very much. This morning I was betting with Jawad on how many people are going to be left, in the audience when it's time to do my presentation. So I won. I'm not going to tell you what I bet. So anyways, the topic of today is a little bit technical of nature. So I'll try to explain it as best I can. But I think giving the mixed audience here between network operators, application developers, and technology providers, I think it's a very good or very important topic to be discussed. Okay, so it's no secret that there is a considerable increase in smartphone traffic that has happened over the past couple of years, and this expected to continue moving forward. I think this is why we are all here today. So basically, the projection is about 4 billion cumulative smartphone sales estimated from 2011 to 2015, peaking at 1 billion smartphones in 2015. And of course, this number of smartphones are driving mobile data demand, which is growing exponentially. Actually, U.S. data usage is expected to grow by 40-fold by 2015. So that's a lot of data, and the figure here is in petabytes, which is 1,000 terabytes. Also, social media is fueling apps usage, and I'm concentrating a little bit about social media for reasons I'll explain a little bit later. But basically, with the uptake of Facebook and other social media applications, the growth of mobile data also, will go even higher. So why is this all important? Everybody is talking about a tsunami of data, and operators were really concerned about how much data volume all of these applications and smartphones are going to be consuming. However, the tsunami that is coming is not really from data. The tsunami is coming from signaling that smartphones are generating over the networks. And this is what operators need to be concerned about. So basically, smartphones applications, they maximize their own performance. They connect freely and frequently to the network, but at a very high cost to the network. And really the root cause of that is that most of our applications are really designed for PC environment. So they're, it's basically taking your Facebook from a PC environment and putting it with the same behavior on your smartphone. And the way wireline behaves is a little bit different than wireless. In wireline, you have almost unlimited resources. You don't need to do any signaling to connect. You're connected all the time, and you always send what they call a stay alive packet. I think a TCP, or we can call it a TCP stay alive packet, which basically generates a very small amount of data that's sent to the network just to keep the application looking as if it is alive or always on. And also because most network operators are dimensioning their network for data volume, not really for signaling. So this signaling issue has been largely ignored until recently, where many operators around the world, they found out that that smartphone signaling is becoming a real problem. So why is it really, what does it impact? I mean, why is it a problem? I mean, first of all, there is really a big increasing process load on the RNC, the radio network controller. And it's the same controller that really handles both voice and data traffic. So if you have shortage of resources because of all this data signaling, then that will impact also your voice usage as well. So you're gonna start seeing voice drop calls and missed pages and things like that. Also, it will impact downlink power. Downlink power also is closely related to the capacity. So you're gonna see that your capacity or your ability to serve multiple users will be diminishing because of that. Also on the handset side, it will impact severely battery life, because the more signaling you are doing, the more connections you're doing, the more battery you are consuming, and this is really of real concern to the operators, because all of this signaling is coming at zero revenue. I mean, they're costing a lot to the operators, but the operators are not seeing any revenue out of it, because the revenue is coming from the data traffic, not the signaling traffic. This is a study that we did, for a network here in the Middle East. And as you can see in the, this color is supposed to be orange. The orange color shows that the number of data connections, how many times a mobile phone is trying to access the network. And on the right-hand side, it shows you again in orange the data consumption for those mobile phones or smartphones. So as you can see that although the majority of those calls are made by smartphones, the majority of data volume is coming from data cards. So the attempts, most of the attempts of the calls are coming from the smartphones, but most of the data generation or the data volume is coming from data cards. Just again attempt here to simplify or explain why this is happening, and then show some potential solutions for it. And the way UMTS works, there are some states that are associated with the connectivity of the mobile to the network. And just for simplicity's sake, I put on the right-hand side, just the simplified notations for those states. So the phone goes from being asleep, which is in the idle state, to going into standby state, to going into this forward access channel, the fetch state, which is a low data rate state, and then the HSPA, which is the high data rate state. And for each of those states, there are some trade-offs, mainly related to the signaling on the network, how much data is being transferred, and on the handset side, how much power consumption the handset is using. So of course, on the sleep mode, the lower state, the power consumption is very low. And of course, on the high end, on this high data rate end, which is, you'll see when you're doing HSPA data at 7.2 or 21 megabits per second, the battery consumption is the highest. So the intention of the standardization process was to really control the way mobiles go from one state to the other. So depending on how much data the mobile is requesting, the network will move it up from sleep to standby to low data rates and to high data rates. Okay, so just to go back, so one of the states, which is the standby state, was supposed to have a very good compromise between the power consumption of the mobile and the signaling on the network. Just to give you an example, going from idle state to the high data rate state on the HSPA state requires about 28 messages. Signaling messages going back and forth between the handset and the network to get there. Going between this standby state to the high data rate state takes only about 7 messages. So there are 4 times, as much signaling happening if you move the phone from sleep to high data rate than standby to high data rates. The problem is that a lot of networks, when they started implementing UMTS, they did not implement this standby state. Maybe because the infrastructure did not support it, or maybe the handsets were not supporting it, or maybe the operators they were not aware of the impact of this feature of this state on the network. So it was largely being ignored. So the original aim was really to get the devices back into this standby state, and if there's really no data transfer at all, going back to idle. But since this standby state is not available, then the phones were going back to idle, and that's creating more signaling on the network. So when some of the device vendors saw that this lack of this PCH state is affecting their battery power, because all of a sudden the users are complaining that whenever they put their phone on 3G, they find out that the batteries will not last them a whole day. So they started complaining to the network providers, and then the network providers complained to the device manufacturers. So the device manufacturers, they wanted to come up with some innovative idea to solve the problem. So what did they do? They came up with this idea of what we call fast dormancy, which means, okay, I'm an iPhone, or I'm any other phone, smartphone. Once I send my last byte from any connection, even if I'm sending 1 kilobyte, I'm just going to go back to idle. No matter what the network tells me to do, I'm just going to send them a release indication without any cause. I'm just saying, okay, I'm sending you a release indication, I'm going back to idle. So 5 seconds later, when the phone wants to send another 10 kilobytes of data, then it will go from idle state to the high data rate state, generating about 30 messages, in the process to send that kilobyte of data, and then again it will go back down to the idle state. Okay.